Welcome to the deep dive. Today we're tackling a challenge that's universally relatable, one that impacts every single one of us, whether you're eagerly awaiting a new gadget or sending a heartfelt gift across the country. We're talking about the incredible logistical puzzle of getting something from point A to point B, swiftly and reliably. Now imagine that challenge scaled up to a vast, incredibly dynamic market like India, where millions of packages crisscross every day. What you might not realize is that behind every successful delivery, every package arriving safely and on time, there's a complex high-tech ballet happening in the background. Okay, let's unpack this. Our subject today is Shiprocket, India's leading logistics and shipping platform. Think of it as a powerhouse, a logistics aggregator that empowers businesses from small startups to large enterprises to truly streamline their entire order fulfillment process. It's handling millions of shipments and over $50 million in financial transactions every single month. That's a huge undertaking. And for this deep dive, our mission is specifically for you, a new computer science student.
We're going to peel back the layers and look at the very core, the back-end architecture of Shiprocket. We'll start from scratch, step by step, explaining how every service, database, and message queue works. Our goal is that by the end of this, you'll not only understand how a complex system like Shiprocket is built and operates at a production scale, but also grasp the foundational knowledge to truly understand and contribute to a system of this complexity.
Indeed. What's truly fascinating here isn't just the sheer volume of transactions, but how they've engineered for massive scale, aimed for, 99.99% availability and maintained uncompromising financial integrity, all while serving incredibly diverse needs in a unique market. As we go through this, we'll explore not just what they built, but why they made those specific technological choices, the trade-offs involved, and what those decisions mean for a system at this level. This way, you get a complete picture, a true peek behind the curtain.
Okay, great. So let's start with the big picture. What exactly is Shiprocket, and what does it do from an operational perspective for businesses? At its heart, Shiprocket simplifies shipping for businesses all across India. Imagine you're a small business owner selling handmade crafts online. Instead of individually negotiating with like a dozen different courier companies, Shiprocket acts as your central hub, making the entire shipping process almost magical.
Precisely. From a business perspective, its core function is to be an intelligent intermediary. It allows businesses to integrate their online stores, whether that's a popular platform like Shopify, a custom-built WooCommerce site, or, a giant marketplace like Amazon directly with the Shiprocket platform. This integration is crucial because it enables seamless order syncing. When a customer places an order on your online store, it automatically appears within Shiprocket ready for processing. This automation extends to generating shipping labels, which are pre-filled with all the necessary details, saving significant manual effort and reducing errors.
Right, and it's not just about getting the package out the door. Shiprocket gives businesses access to a wide network of courier partners, so you as a seller aren't locked into just one. You can choose the most suitable courier based on factors like how fast you need it to get there, how much it will cost, or what areas they cover. After that, the platform generates those shipping labels we mentioned and your package is ready to go. But the journey doesn't end there, does it?
Exactly. Post-dispatch, Shiprocket offers real-time order tracking. This is a huge benefit for both the business and the end customer. Everyone can monitor the shipment's progress from the moment it leaves the warehouse until it reaches its destination. Beyond that, for any returns or exchanges, Shiprocket streamlines what's called reverse logistics. It provides return labels and manages that entire return journey, which can be quite complex in a traditional setup. Finally, the platform provides businesses with valuable insights through analytics and reports. This data covers everything from delivery timelines and costs to customer satisfaction, helping businesses optimize their strategies and improve overall efficiency.
So if we look at the key benefits for a business using Shiprocket, it really boils down to several crucial points. First, reduce shipping costs. Because Shiprocket aggregates so much volume, they can negotiate better rates with multiple courier partners, and those savings get passed on. Makes sense. Second, increase delivery speed. A wider network of partners means more options and often faster, more reliable deliveries, which is essential for customer satisfaction.
Absolutely. And that leads directly to the third benefit, improved customer experience. Real-time tracking and timely deliveries are fundamental to customer satisfaction in e-commerce today. Fourth, simplified operations. Automating tasks like label generation and order tracking truly streamlines a business's daily operations, freeing up time and resources. And fifth, enhanced visibility. Detailed analytics and reports provide clear insights into shipping performance, allowing businesses to make data-driven decisions. In essence, Shiprocket acts as a valuable tool, helping businesses improve efficiency and gain a competitive edge. The key takeaway for us as we explore the back end is understanding that every one of these business benefits is directly underpinned by a carefully designed and robust technical architecture.
That context is vital because it explains why the back end is designed the way it is. Now let's talk about the core philosophy that guides Shiprocket's back-end architecture. We have a building for massive scale, aiming for 99.99% availability, and maintaining uncompromising financial and data integrity. These aren't just a wish list, these are the non-negotiable foundations. To put it into perspective, during peak seasons, the platform processes anywhere from 3 to 5 million shipments daily, with financial transactions exceeding $50 million monthly. That's a tremendous amount of data and activity to handle.
It truly is. To achieve that, the architecture is fundamentally cloud native. This means it's designed from the ground up to run specifically in the cloud, leveraging cloud services for scalability, resilience, and operational efficiency. And it's built on a domain-driven microservices paradigm. For you, as a new computer science student, this is a critical concept. Instead of one massive, monolithic application, Shiprocket's functionality is broken down into many smaller, independent services. Each of these microservices focuses on a specific business domain, like orders, payments, or tracking. This approach is fundamental for scalability, as individual services can be scaled independently, and for maintainability, as teams can work on different services without stepping on each other's toes.
And what's really smart is their commitment to a unified technology stack. For the back end, they've standardized on Java 21 with Spring Boot 3. This isn't just about preference, it significantly reduces complexity. When everyone is speaking the same technological language, it standardizes development, makes it easier for engineers to move between teams, and simplifies tooling and operational support.
Exactly. And for a system of this scale, consistency is paramount. Their commitment to Java 21 with Spring Boot 3 isn't just about picking a popular stack, it's a strategic move. The real insight here is how it minimizes cognitive load for the rapidly scaling engineering teams, especially in a market with abundant Java talent. It allows them to focus intensely on complex business logic and innovation rather than grappling with framework inconsistencies or diverse tooling.
Yeah, consistency is key in such a large system. Now let's delve into the guiding architectural principles, what we might call the Shiprocket doctrine. The first and perhaps most foundational principle is domain-driven design, DDD, as law. This means the system is rigorously decomposed into microservices that represent clear, unambiguous business domains. But for someone new to microservices, how would you quickly define bounded context in like a single sentence before we dive into how Shiprocket uses it?
That's a great question. Think of a bounded context, like a specialized department in a company. Each department, say HR or finance, has its own clear scope, its own language, and its own rules. They don't try to be experts in everything. In software, a bounded context is a clearly defined boundary around a specific business domain like authentication or orders. Within that boundary, a microservice is the definitive authority, owning its data and logic. This clarity prevents confusion, makes the service easier to manage, and ensures that a change in finance doesn't accidentally break HR. For Shiprocket, this means 27 distinct service domains, each with a precise boundary like auth service, payment service, order service, and tracking service. This strict separation of concerns isn't just an academic exercise, it's the bedrock for scalability, maintainability, and organizational agility. When a service is focused on a single, well-defined domain, it's easier to develop, test, deploy, and scale independently.
That makes a lot of sense. If you have clear boundaries, you know exactly where a piece of logic should live. Okay, next up are the communication patterns. Synchronous for immediacy, asynchronous for throughput. It sounds like they're being very deliberate about how services talk to each other.
Exactly. They follow a clear bifurcation. For synchronous communication, meaning operations that demand immediate feedback and are often user-facing and latency-sensitive, think creating a single order or generating a label, Shiprocket uses gRPC. Now, you might be familiar with REST APIs, but for internal service-to-service communication, gRPC offers significant advantages. It provides superior performance due to its use of protocol buffers for data serialization, which are much more compact than JSON. It also enforces a strict schema, meaning you define the structure of your messages up front, which helps prevent compatibility issues. Plus, gRPC supports streaming, which can be useful for certain types of data exchange, making it ideal for the internal nervous system of the platform.
Right, so gRPC is all about speed and strict contracts for those internal calls. What about asynchronous communication then?
For asynchronous communication, which is ideal for high-throughput, deferrable, or decoupled workflows, they rely heavily on Apache Kafka. This is the backbone for tasks like bulk order ingestion, where you might have thousands of orders coming in at once and don't need immediate synchronous feedback for each one. It's also used for notifications, analytics, data pipelines, and general interdomain events. This event-driven approach ensures resilience because if one service is temporarily down, Kafka acts as a buffer, preventing messages from being lost and allowing services to scale independently as they consume messages at their own pace. The key insight here is choosing the right tool for the right job, balancing immediate feedback with system throughput and resilience.
This brings us to another fascinating principle: pragmatic and purpose-fit consistency. This sounds like they're rejecting a one-size-fits-all approach to how data remains consistent across the system.
They absolutely are. Instead of enforcing one consistency model everywhere, they apply the appropriate model to each domain, considering its specific throughput requirements and operational realities. Let's take the finance domain as an example. For financial operations, which demand the highest integrity, they use a hybrid consistency model with safety nets. This is a two-phase approach. The first is the reservation phase, used for initial fund reservations, like when an order is created. Here, they use optimistic locking with versioning to allow for high throughput. This means multiple transactions can attempt to update a record simultaneously, and conflicts are detected by checking a version number. If versions mismatch, one transaction retries.
Okay, so optimistic locking allows for a lot of activity without blocking, which sounds great for throughput, but what about the actual movement of money? That needs to be absolutely rock solid, right?
That's where the second phase, the settlement phase, comes in. For actual fund movement, the captures and reversals, they use strict serializability with fine-grained locking. This is the strongest form of isolation, ensuring that transactions appear to execute one after another, preventing any concurrent updates from causing inconsistencies. And crucially, this locking is on individual ledger entries, not entire accounts, which helps maintain concurrency even with strict consistency. To further enhance financial integrity, they have compensating transactions with dead letter Q, DLQ handling. This means if a multi-step financial operation partially fails, a compensating transaction automatically triggers to undo prior steps. If even the compensating transaction fails, it goes to a DLQ for manual review, ensuring no financial transaction is ever lost or left in an inconsistent state. The key insight for you as a new CS student here is understanding that consistency isn't a single switch, it's a spectrum, and choosing the right level is a critical architectural decision driven by business needs.
Wow, that's incredibly thorough. What about other domains like general business logic, orders and things?
For the business logic domain, encompassing high-throughput entities like orders, they again use optimistic lock-in with conflict resolution. This version-based approach maximizes concurrency. When an object optimistic locking failure exception occurs, meaning another transaction updated the data you were working on, the service catches it and retries the operation with the latest data. This is vital for scenarios like concurrent inventory updates for the same product. Okay, imagine you and I are both trying to update the same order at the exact same time. If we use traditional locking, one of us would have to wait, which slows things down. That's where optimistic locking comes in, and it's brilliant for maximizing concurrency. Think of it like a version control system. When you update an order, you're essentially saying, I'm making changes to version 5. Whoa. If someone else simultaneously tries to update version 4, the system says, hold on, that's an old version. It catches that conflict and instead of blocking, just tells your service to grab the latest version and try again. This way, valid updates almost always succeed without constant waiting, making the system much more responsive, especially during peak load.
Got it. And for data that might be spread across multiple locations or needs to be eventually consistent, like inventory levels, that seems tricky.
For the synchronization domain, which often deals with eventually consistent data like inventory, they use versioned conflict-free replicated data types, or CRDTs. Instead of simple last write wins, LWW, which can lead to data loss due to clock skew in distributed systems, CRDTs with vector clocks provide stronger guarantees. Vector clocks allow the system to understand the causal history of updates, ensuring that even if updates arrive out of order or from different replicas, they can be merged correctly without losing data. This is critical for maintaining an accurate, globally consistent view of inventory. The big takeaway here is that in complex distributed systems, you can't always just take the latest update. You often need to intelligently merge changes to prevent data loss.
It really sounds like they're leaving no stone unturned. The last principle, operational completeness as a requirement, Really ties it all together, doesn't it?
Indeed. This isn't just about building functional services, it's about building production-ready services. Every single service must include detailed operational considerations, robust failure handling patterns, and a comprehensive reliability testing strategy. A service is simply not considered production-ready without these elements, emphasizing that reliability and operational resilience are built in from day one. This proactive approach saves countless headaches down the line.
That's a strong doctrine. Now let's go even deeper into the actual building blocks, the unified backend technology stack. This is the toolkit every backend developer at Shiprocket uses.
Yes, and this stack is standardized for a reason. For the application framework, they're using Java 21, Spring Boot 3.2.x, and Spring Cloud 2023-20.0. Spring Boot is an incredibly mature and robust ecosystem, perfect for building enterprise-grade microservices. Within this, they leverage Spring Data JPA with Hibernate 6.4 for seamless interaction with relational databases. For asynchronous messaging, they use Spring for Apache Kafka, configured for exactly once semantics, which means each message is processed once and only once, even if failures occur. That's a big deal. And for security, it's Spring Security with JWT, JSON Web Tokens, and OAuth2 for secure authentication.
Yeah, exactly. Once semantics for Kafka is huge, ensuring reliability and event processing. And there's a crucial enhancement here too, right, with retries.
Absolutely. A crucial enhancement is Spring Retry, configured with exponential backoff for all service-to-service calls. In a distributed system, transient failures, temporary network glitches, or brief service unavailability are inevitable. Spring Retry automatically retries these calls, waiting a bit longer each time, which vastly improves the system's resilience without requiring developers to write complex retry logic in every service. It's like having a patient, persistent assistant built directly into your code.
So for structured data, the important stuff like orders and finance, what's their primary database of choice?
For transactional databases, they rely on Amazon RDS for PostgreSQL 16.2 plus SYN with a crucial enhancement, PG Bouncer. PostgreSQL is chosen for its ACID compliance, ensuring atomicity, consistency, isolation, and durability, which is essential for transactional data where every financial and order detail must be perfectly preserved. The enhancement, PG Bouncer, is a connection pooler configured at the service level. This is vital because managing a large number of database connections can be resource-intensive for the database itself. PG Bouncer sits between your Spring Boot services and PostgreSQL, pooling and reusing connections, preventing database connection exhaustion during traffic spikes and maintaining performance. It's like having a bouncer at a club, making sure the VIPs, your services, always get a table without overwhelming the venue.
Okay. And for high throughput, less structured data, where speed is maybe more important than complex relationships.
For key-value databases, they selectively use Amazon DynamoDB with global tables. This is for specific, high-throughput, low-latency workloads that naturally fit a key-value model, such as inventory tracking, where you need to quickly get or update an item by its ID. The key here is the selective use. It's not a general-purpose database, but specialized for specific high-demand scenarios. The Global Tables feature provides multi-region replication for disaster recovery. If one AWS region goes down, your data is available in another, which is a significant leap for business continuity. However, with multi-region rights, application-level conflict resolution becomes necessary, which is handled in the inventory sync service using CRDTs, as we discussed.
Right, makes sense. Caching is always a big part of performance. What are they using there?
For caching and locking, they use Amazon Elasticache for Redis 7.2 Plus in cluster mode with multi-AZ deployment. Redis is incredibly versatile, used for high-performance distributed caching to speed up data retrieval. Think product details or common query results. Session storage for user logins, rate limiting to protect services from abuse, and for implementing distributed locks, which are crucial for coordinating actions across multiple service instances. The cluster mode deployment means it's not just one Redis instance, it's spread across many, ensuring both high availability, if one part fails, others are available, and horizontal scalability, capable of handling immense loads. They even perform weekly automated failover testing to ensure its resilience.
Wow, automated failover testing, that's serious. And for the messaging backbone, Kafka again.
Yes. The central nervous system for all asynchronous communication and eventing is Amazon MSK, Managed Streaming for Kafka 3.7 Plus. This provides a durable, high-throughput, distributed log for everything from event sourcing to data pipelines. The key insight for you as a new CS student is understanding that Kafka isn't just a queue, it's a persistent, ordered log of events, allowing services to communicate reliably and process data at their own pace. Shiprocket's MSK cluster is robustly configured with 30 brokers across 6 availability zones, replication factor of 3 for critical topics. This achieves immense resilience against zone failures and ensures data durability, meaning even if multiple parts of the cloud infrastructure go down, your critical event data isn't lost and message processing continues.
Okay. Finally, how do all these services communicate with the outside world and each other? Just to summarize the protocols.
For webhook endpoints and communication, the pattern is clear. REST APIs are used for external-facing APIs and webhooks that interact with other systems outside Shiprocket. Think talking to an e-commerce platform or a payment gateway. gRPC, as discussed, is exclusively for internal, high-performance service-to-service communication, keeping that internal chatter fast and efficient. And Kafka serves as the backbone for asynchronous eventing, decoupling services, and enabling independent scaling, vital for the overall health of the system.
All right, let's transition to part 2. We're focusing on the infrastructure that supports our backend services, specifically framed for you, the backend developer. While we're not diving super deep into DevOps today, it's crucial for you to understand the environment where your Spring Boot microservices run and how it directly impacts their performance and reliability. We're talking about Amazon EKS, Istio, and the security layers, but we'll focus on what you as a developer need to know to make your Spring Boot microservices hum.
Indeed. For backend developers, Amazon EKS, Elastic Kubernetes Service, serves as our runtime environment. Its core function is to provide a managed Kubernetes control plane. What this means for you is that EKS abstracts away the complexities of managing the underlying server infrastructure. You don't have to worry about maintaining servers, patching operating systems, or ensuring the availability of the Kubernetes control plane itself. EKS handles all of that, ensuring a highly available environment where your Spring Boot services run reliably.
So it's essentially a highly available playground for your code.
Mm-hmm.
What are the key configuration aspects that affect a backend developer directly?
First, multi-AZ deployment. Our EKS clusters run across multiple AWS availability zones, actually 4 in the App South 1 region. This is crucial because it means instances of your Spring Boot service are automatically spread out across different data centers. If one data center experiences an outage, your service remains available because other instances are running in unaffected zones. It's a fundamental aspect of designing for failure at the infrastructure level.
Right, basic high availability. What about managing resources for your actual service instances, your pods? That seems important for performance.
Absolutely. That's handled by resource management for pods. Every single Spring Boot application deployment must include precisely defined CPU and memory requests and limits. This isn't optional, it's a non-negotiable requirement. Requests tell Kubernetes how much CPU and memory your pod needs to function, which helps with scheduling. Limits cap how much your pod can consume. This predictability is vital for stable performance and ensures that one runaway service doesn't starve others of resources. It's about being a good neighbor in a shared environment.
Okay, makes sense. And how does Shiprocket ensure services scale automatically when demand spikes, like during those big festival sales?
We use 2 main mechanisms. Horizontal pod autoscalers, HPAs, are configured for every service. HPAs automatically increase or decrease the number of pods, instances, of your Spring Boot service based on load, typically targeting an average CPU utilization of 70%. If your service's CPU usage goes above that, more instances are spun up. Conversely, if it drops, instances are scaled down. Then, for stateful services like the account service, which cannot easily scale horizontally due to database contention, we use vertical pod autoscalers, VPAs. VPAs dynamically adjust the CPU and memory allocated to individual pods, rather than changing the number of pods. This helps optimize resource allocation for services that benefit more from larger individual instances.
And for really critical services, like those handling financial transactions, how do you ensure their performance isn't impacted by other, maybe less critical workloads running nearby?
That's addressed by node affinity and taints for critical services. We deploy critical financial services on dedicated node groups within EKS. These node groups have taints, which basically prevent other, less critical backend workloads from being scheduled on them. This ensures their isolation and guarantees that they have the dedicated resources and performance they need without interference. It's like having a dedicated high-security wing for your most sensitive operations.
Okay, that covers where your code runs.
Yeah.
Now let's talk about how your backend services communicate securely and reliably with each other, the Istio service mesh. For a backend developer, what's the most important thing to understand about Istio?
The core function for you as a backend developer is this. Istio's Envoy proxy sidecar is automatically injected into every Spring Boot application pod. This sidecar is transparent. It intercepts all network traffic to and from your service. What's revolutionary here is that it allows centralized control over service-to-service communication without requiring any code changes in your Spring Boot application. You don't need to add specific Spring Cloud libraries for things like circuit breaking. Istio handles it at the infrastructure layer, making your service inherently more resilient.
So it's like a transparent communication bodyguard for every one of your services. What specific intelligent traffic management and resilience features does Istio provide for your backend calls?
Two critical examples stand out. First, adaptive circuit breakers. Istio automatically adjusts the thresholds for back-end service calls, for example, calls made by your courier service to external carrier APIs based on historical performance. If a carrier API starts slowing down or failing, Istio can proactively eject those slow or failing endpoints from the load balancing pool, preventing your service from trying to send traffic to them and thus preventing cascading failures across the system. Your service remains responsive because Istio has intelligently identified and isolated the problem.
That's fantastic for protecting against flaky external dependencies and for testing new versions of critical services. How do you do that safely?
For critical financial services, we use traffic mirroring for production testing. This allows us to duplicate live production traffic and send it to a new backend version in parallel without impacting live users. You can observe how your new service version handles real-world load and data before a full rollout. This is invaluable for validating critical changes with absolute confidence. And on the security front, Istio provides mutual TLS, MTLS, by default, ensuring all communication between your back-end services is encrypted and authenticated without extra effort from the developer.
That's a huge benefit for security, just handled automatically. Let's move to the platform security layer for back-end services. As a back-end developer, you're constantly dealing with sensitive data and credentials. How does Shiprocket manage secrets securely?
For secrets management, all sensitive back-end secrets database passwords, API keys for external services, signing keys are stored securely in AWS Secrets Manager. To make these available to your Spring Boot services running in Kubernetes, we use the AWS Secret Store CSI driver. This driver allows Kubernetes to mount these secrets as files directly into your Spring Boot pods at a specified path, say Vent Secrets. Your Spring Boot application then reads its configuration from these mounted files. The crucial aspect here is that these secrets are never exposed as environment variables or embedded in container images, significantly reducing security risks. As a crucial measure, these secrets are automatically rotated every 90 days using a dual-phase, zero-downtime process, ensuring credentials remain fresh and secure.
Okay, so secrets are handled automatically and securely, mounted as files. What about network access between services? How do you prevent service A from talking to service C if it shouldn't?
For network access, we adopt a deny-by-default approach using Kubernetes network policy. This means, by default, no backend service can communicate with any other. Each backend service must have an explicit network policy that whitelists only the necessary inbound traffic sources. For instance, the account services policy would only allow traffic from the order service and label service, dropping all other unauthorized traffic. This creates a strong, granular security perimeter around each microservice, a critical defense in-depth strategy.
Makes sense. Least privilege for network traffic. And for accessing other AWS services like S3 for storing labels or DynamoDB for inventory, how do services get credentials for that?
That's where IAM roles for service accounts, IRSA, come in. Instead of static, long-lived AWS access keys, each Kubernetes service account, which is associated with your back-end service pods, is linked to a specific AWS IAM role. This grants your pod secure, temporary AWS credentials to access other AWS services, and critically, these permissions are scoped to the absolute minimum required for that service's function, adhering to the principle of least privilege. No long-lived keys floating around.
Okay. Finally, what about the heightened security needed for external payment webhooks? Those seem like prime targets.
Payment webhooks, especially for financial services, require multi-layered security. First, signature validation uses HMAC SHA-256 with regularly rotated keys to ensure the request truly came from the expected payment gateway. Second, idempotency handling uses the Redis cluster for idempotency keys to prevent duplicate processing of the same webhook event, even if it's sent multiple times. This is critical for finance. Third, rate limiting is enforced using AWS WAF rules, protecting these critical endpoints against DDoS attacks. And fourth, request validation is applied, where all webhook payloads are rigorously validated against Avro schemas before any processing begins by the backend services, ensuring data integrity from the start.
Right, multiple layers of defense. All these layers contribute to a robust security posture. Now, let's talk about chaos engineering and reliability practices. For a back-end developer, what does it mean that reliability is a core engineering practice? It's not just testing, right?
Exactly. It means reliability is baked in, not bolted on. Chaos engineering is a discipline where we intentionally inject failures into the system to find weaknesses before they cause real outages. These chaos experiments are run at multiple levels. At the application level, for example, simulating a specific method failing in your Spring Boot service. At the service mesh level, for example, introducing network latency between your services via Istio. And at the infrastructure level, example, simulating a database failover.
And how is this integrated into the development cycle? Is it just something done occasionally?
No, it's continuous. We have an automated chaos testing pipeline. Chaos experiments for your backend services are defined in Git as YAML files, version-controlled like code. They are validated during CI, then run in staging environments to test new versions before deployment. Crucially, these experiments are even run in production during off-peak hours, but in a controlled manner, with automated analysis of the results to identify and fix vulnerabilities in your services before they impact users significantly.
That's a brave approach, running chaos in production. But it sounds incredibly effective for building confidence. What are some critical chaos experiments for financial services that directly test back-end resilience?
For financial services, we specifically simulate scenarios like PostgreSQL master failures during critical financial operations, or Redis cluster failovers during payment processing. We might simulate network partitions between the order service and the account service during an order placement. These directly test the resilience of your backend financial logic and data integrity under failure conditions, ensuring that our compensating transactions and consistency models hold up when it matters most. It's about proving that your financial systems can withstand the unexpected.
Okay, this brings us to part 3, where we dive deep into Shiprocket's microservices themselves, the back-end logic in action. This is where you, as a computer science student, will really see how all those architectural principles come to life in specific services. Let's start with the gateway, the authentication session domain, specifically the auth service.
Right, the auth service. Its bounded context defines it as the definitive authority on seller identity, authentication, and API access control. It's a mission-critical service designed for low latency and 99.99% uptime because virtually every interaction with Shiprocket requires authentication.
So what does its back-end logic look like for, say, a seller logging in? Walk us through that.
For authentication, it uses the Spring Boot Starter Security Module, which is pretty standard for securing Spring applications, integrated with JWT JSON Web Tokens. When a login request comes in, the service's user detail service implementation loads the seller's details, including their encrypted password, from the PostgreSQL database. The bcrypt password encoder then securely compares the provided password with the stored hash. If they match, authentication is successful. Pretty standard flow, but critical.
And that leads to generating the JWT itself. How is that structured?
Yes. Upon successful authentication, it uses the io.jsonwebtoken.jwt library to construct and sign a JWT. This token contains crucial claims, which are basically pieces of information embedded within it: seller ID, expiration time, usually short, like 15 minutes for access tokens, roles, permissions, and a unique JP or JWT ID, which is important for revocation. It also distinguishes between these short-lived access tokens and longer-lived refresh tokens, typically valid for 7 days.
Okay, so you have a short-lived access token and a longer-lived refresh token. How is that refresh process handled, especially to keep it secure?
This is where token refresh with enhanced security comes in. Shiprocket implements token rotation. When a seller uses their refresh token to get a new access token, the system issues both a new access token and a new refresh token. Crucially, it simultaneously invalidates the old refresh token that was just used. This significantly enhances security because even if an old refresh token is compromised somehow, it becomes useless very quickly.
Smart. What if a token needs to be immediately invalidated, like if a user explicitly logs out or maybe their account is compromised?
For token revocation, the auth service maintains a Redis cache of revoked token IDs, JS, with a TTL, time to live, that matches the token's remaining lifetime. So revoked tokens eventually expire from the cache naturally. To efficiently check for revoke tokens in high-volume scenarios without hitting Redis for every single request, it also uses a Bloom filter. A Bloom filter is a probabilistic data structure that can very quickly tell you if an item might be in a set, so you should check Redis, where it's definitely not in the set, so you can skip the check. This provides very fast, memory-efficient checks for revocation.
Beyond tokens, how does it harden overall security against attacks?
It includes security hardening measures like rate-limiting login attempts, maybe 5 per minute per IP address. After a certain number of failed attempts, say 10, the associated account is automatically locked for a period to prevent brute force attacks. Basic but essential hygiene.
Okay, so the auth service gets sellers in the door and keeps them secure. But once they're in, they need to actually run their business, getting orders from their online stores into Shiprocket. That sounds like a massive integration challenge with so many different e-commerce platforms out there. How does Shiprocket tackle that without drowning in complexity? Let's talk about the platform integration domain, specifically the platform sync service.
It absolutely is a challenge. Its bounded context is the central hub for integrating with external e-commerce platforms like Shopify, Amazon, WooCommerce, Magento, eBay, you name it. And it's responsible for synchronizing essential data such as orders, inventory, and tracking information between those platforms and Shiprocket. Without this, Shiprocket couldn't act as the aggregator it is. Its value proposition depends on this.
What's the core logic for how it gets data from all these diverse platforms? Does it constantly ask them for updates?
It primarily uses two methods. The preferred method is webhook-based synchronization. Many modern e-commerce platforms can send real-time events or webhooks to a designated URL when something happens, like a new order being placed or inventory changing. The platform sync service exposes a specific endpoint, like POST v1 intern webhooks platform type, to receive these events. This is far more efficient than constantly polling as it's event-driven. However, for platforms without robust webhook support or as a fallback, it uses polling-based synchronization, where it periodically calls the platform's API at configured intervals to check for new data, new orders, updated inventory, etc.
So it adapts based on the external platform's capabilities. That makes sense. How does it handle all the different data formats it receives? Shopify's order format must be different from Amazon's.
This is a crucially important piece of its logic: order normalization. It transforms the diverse order formats received from different platforms into a unified normalized order Avro schema. Avro schemas provide a compact, fast, binary serialization format and a well-defined contract for the data, managed by a central schema registry. Once normalized, this Avro message is produced to the normalized orders Kafka topic, making it consumable by other internal Shiprocket services like the order service. This normalization step is a key insight. It allows Shiprocket to treat orders from any platform the same way internally, vastly simplifying downstream processing. It decouples the internal logic from the specifics of external platforms. It also pushes tracking updates back to the original platform API.
Now we enter the finance domain, which is inherently sensitive and requires extreme precision. We'll look at two critical services here, the payment service and the account service. Let's begin with the payment service.
The payment service's bounded context establishes it as a highly isolated and secure service, acting as the sole intermediary with external payment gateways like Razorpay, PayU, etc. It's responsible for managing wallet recharges, cash on delivery, COD settlements, and payment reconciliation. This isolation is a key security measure. Other services don't talk directly to payment gateways.
Okay. How does it handle initiating a payment, like when a seller wants to add funds to their Shiprocket wallet?
When a seller initiates a wallet recharge via a REST endpoint, the request typically includes the amount, payment method, like UPI, card, net banking, and a callback role. The service first generates a unique transaction ID, a UID, persists this transaction with a pending status in its PostgreSQL database. Then it uses the external payment gateway's Java SDK to create a payment session or order with the gateway. Finally, it returns a redirect URL or perhaps a UPI intent string to the seller's front end, allowing them to complete the payment on the gateway's secure page or app.
Right. And once the payment is completed successfully on the gateway side, how does Shiprocket get confirmation? This is where those webhooks come in again. And given its payments, security must be absolutely paramount.
Exactly. Webhook processing is at the heart of payment confirmation, and it's built with multiple layers of security and reliability. First, rate limiting is applied via AWS WAF to limit webhook calls per source IP, protecting against flood attacks. Second, Signature validation is performed using HMSC SHA-256 with regularly rotated secret keys shared between Shiprocket and the gateway, verifying the webhook's authenticity. Third, for idempancy check, it uses the Redis cluster. The gateway usually includes a unique identifier for the event in the webhook payload. The payment service uses this as an idempancy key, checking Redis to ensure that if the same webhook is received multiple times, which can happen, it's processed only once. This is critical to prevent double crediting funds. Fourth, request validation occurs, where all incoming webhook payloads are rigorously validated against predefined adverse schemas before any processing begins. If the event is new, authentic, and valid, the service updates the internal transaction record in PostgreSQL to successful and, importantly, produces an Avro message containing the transaction details to the wallet recharges Kafka topic.
That's a lot of checks, but absolutely necessary for payments. Now let's move to the account service, which sounds like the ultimate financial ledger for Shiprocket, prioritizing consistency above all else.
This is indeed the definitive source of truth for all seller funds, and its bounded context emphasizes consistency above availability and performance, but with sophisticated engineering to achieve high throughput simultaneously. It's the core ledger.
How does money actually get credited to a seller's account after that Kafka message is produced?
For wallet crediting, a Kafka listener, specifically configured with manual acknowledgement, consumes messages from the wallet recharges topic. The entire processing logic, from reading the message to updating the seller's balance in the database, is wrapped within a single database transaction. This, combined with the Kafka configuration, ensures exactly once processing semantics. This means if the service crashes after receiving a message, but before committing the database change and acknowledging the message to Kafka, it will reread and reprocess the message upon restarting. But the database transaction ensures the balance isn't double credited. This is a critical reliability feature for any financial system.
Yeah, exactly. Once processing is vital.
Yeah.
Tell us more about the hybrid ledger architecture. This sounds complex but important.
It is, and it's a final, crucial implementation detail reflecting lessons learned. First, the ledger database, PostgreSQL, is sharded by seller ID at the application level. This means instead of one massive database trying to handle all sellers, sellers are distributed across multiple PostgreSQL instances based on a consistent hashing algorithm applied to their seller ID. Each shard handles a subset of sellers, and these shards can be dynamically rebalanced based on load, usually during off-peak hours.
Okay, so sharding helps distribute the load across multiple databases, but how do they maintain consistency given that high throughput is also a goal, especially for reserving funds when orders come in?
This is achieved through a clever two-layer consistency model. The first layer is the reservation layer. When an order is created, funds need to be reserved to ensure the seller can pay for shipping. This initial reservation uses optimistic locking with versioning on the account balance record. This allows for high throughput because multiple reservation requests can proceed concurrently without blocking each other initially. Reservations are typically valid for a limited time, say 24 hours, and automatically reversed if not captured. For example, if the order is canceled before shipping.
So reservations are fast and optimistic. What about the actual money movement?
Yeah.
Capturing funds or refunding?
That's the settlement layer. Actual fund movements, such as capturing reserve funds after a successful shipment or reversing funds for a canceled order, use strict serializability with fine-grained locking. Unlike locking the entire account record, which would severely limit concurrency, fine-grained locking applies to individual ledger entries being created for the transaction. This allows multiple capture or reversal operations to proceed concurrently for different transactions related to the same seller account, while still maintaining absolute financial integrity by ensuring that these critical fund movements happen sequentially from a logical perspective within the database transaction.
That's a very nuanced approach. And what if something goes wrong during these multi-step financial operations involving reservations and captures?
This is handled by compensating transactions with a dead letter queue, DLQ. The system implements a saga pattern to ensure financial integrity for distributed transactions that span multiple services or steps. If a multi-step workflow partially fails, e.g. a payment succeeds but the subsequent label generation fails, the system automatically triggers compensating transactions to undo the prior successful steps, like reversing the fund reservation. If a compensating transaction itself fails, which should be rare but possible, it's routed to a dedicated compensating transactions DLQ Kafka topic. This DLQ is critical. It's monitored and processed manually by the financial operations team, ensuring no financial inconsistency is ever left unaddressed. For example, if payment succeeds but label generation fails, the reservation is automatically reversed after maybe 30 minutes. All financial operations also publish events to a financial events Kafka topic for audit and reconciliation purposes, and a dedicated reconciliation service runs hourly to proactively detect and help resolve any inconsistencies that might slip through. This level of detail for failure handling in finance is absolutely critical.
That's an incredibly robust financial core. It really shows the emphasis on integrity. Let's shift gears now to the core logistics and fulfillment domain, starting with the address validation and locality service. In a country like India, accurate addresses must be a huge challenge.
They are, absolutely. And this service's bounded context defines it as the authoritative source for address validation, PIN code verification, and locality information. It's absolutely critical for determining serviceability, can we ship there, and ensuring accurate shipping costs and delivery times. The key insight here is that in a diverse market like India, address data is not always clean or standardized, so robust validation is not just a nice-to-have, but a core requirement for successful logistics.
How does it actually perform address validation? It sounds like it needs to be more than just checking if the format looks right.
It is a sophisticated, multi-stage process. First, syntax validation checks the address format against regional patterns. Then, PIN code verification validates the PIN code against the latest India Post database. Beyond basic validation, it employs machine learning as part of the Sense Address API, which we'll touch on later, for address scoring, assigning a confidence score to the address based on its likelihood of being deliverable using historical data and patterns. Finally, it performs standardization, normalizing address components like street names, city names, to a consistent canonical format, which helps downstream systems.
And it needs to manage a vast amount of PIN code data, right? Like which areas are serviceable.
Yes, it handles PIN code database management by maintaining a local copy of India Post data, which is updated daily. This database is rich with information, including delivery office details, serviceability information for major carriers operating in that PIN code, zone information used for shipping cost calculations, and regional restrictions, such as remote areas requiring special handling or documentation. For geographical querying, like finding all PIN codes within a certain delivery zone, it leverages geospatial indexing, using PostGIS extensions within PostgreSQL to store and query geographic boundaries efficiently.
So it knows which carriers serve which areas and maybe specific constraints.
Precisely. It maintains carrier-specific serviceability rules for each PIN code. This includes crucial details like whether cash on delivery, COD, is allowed by a specific carrier in that area, maximum weight or dimensional restrictions for packages, available service types, for example, express, standard, surface, and estimated delivery timelines, EDDs, based on the origin and destination PIN codes. This data feeds into the courier selection logic.
Okay. Moving on to the courier service. This sounds like the central nervous system for all carrier interactions, especially since Shiprocket deals with 15+ different carriers, each with their own APIs and rules.
It is indeed. Its bounded context is the comprehensive management system for all carrier capabilities, rates, serviceability, and the actual integrations. It handles the complexities of integrating with over 15 carriers, each with varying API standards, using a robust gateway per carrier model. This is a really important design choice.
What exactly does that gateway per carrier model entail? That sounds like a crucial detail for minimizing risk and complexity.
It's a design pattern chosen specifically to minimize the blast radius of a failure and simplify development. The main courier service acts as a router and aggregator. It doesn't implement the specific API logic for each carrier directly. Instead, separate microservices, known as carrier adapter services, are created for each individual carrier or maybe a small group of similar carriers. For instance, you'd have a FedEx adapter service, a DTDC adapter service, a delivery adapter service, and so on. The key insight here is that if one carrier's API integration fails or becomes slow, it only impacts its specific adapter service, not the entire courier service or the wider Shiprocket platform. This prevents a single external dependency from crippling the entire system. It also allows teams to specialize in specific carrier integrations.
Right, so the main courier service routes request to these independent adapter services. How does it find them and talk to them?
It uses Istio's service registry for service discovery to dynamically find and route requests, usually via gRPC, to the correct carrier adapter service based on the chosen carrier ID. This abstraction means the courier service doesn't need hardcode knowledge of where each adapter lives. Istio handles the routing.
And what about managing all the API keys, credentials, specific rate cards, and business rules for each of these 15-plus carriers? That must be a massive management overhead.
That's handled by a carrier configuration service, which is a critical enhancement. This is a dedicated service, possibly with a UI, that allows business operations teams, not engineers, to manage all carrier settings, API keys, endpoint URLs, credentials, rate tables, specific serviceability rules, label formats, etc. It provides versioning for all configuration changes, maintains audit trails for accountability, and, crucially, allows the adapter services to dynamically reload their configuration without needing a restart or redeployment. This means updates to a carrier's API keys or changes in their business rules can be deployed quickly and safely without downtime, a huge operational advantage.
Okay, that structure makes a lot of sense for managing complexity. Let's move to the order service. This seems like the heart of Shiprocket, managing the entire journey of a customer's order once it's inside the system.
It certainly is a core service. The order service's bounded context is to manage the life cycle of an order from its ingestion into Shiprocket, after normalization by platform sync, to its readiness for fulfillment, label generation. This includes comprehensive state management and robust failure handling.
How does it manage the different stages an order goes through, like from pending to shipped?
It implements a formal order state machine using libraries like Spring State Machine. This manages order statuses such as pending acceptance, processing, ready to ship, shipped, delivered, or canceled. This state machine defines valid transitions. For example, you can't go directly from pending to delivered, ensuring that orders move through their life cycle logically and preventing invalid status changes. Actions trigger state transitions.
So when an order comes in from, say, the platform sync service via that Kafka topic, what's the workflow?
That's the order ingestion workflow. The order service listens to normalized order events from the normalized orders Kafka topic. Upon receiving an event, 1, it creates an order record in its own PostgreSQL database, which is sharded by Celerid. 2, it makes a synchronous gRPC call to the account service to reserve the necessary balance for the estimated shipping cost. If the reservation fails, for example, insufficient funds, the order might be moved to an unhinged to sold state. 3, it makes another synchronous gRPC call to the inventory sync service to update inventory, effectively reserving the items in the order. If inventory isn't available, the order might also go on hold or fail. 4, assuming reservation and inventory checks pass, it transitions the order state of FAIR-EG to processing or ready to ship and publishes an order created event or order ready to ship event to a Kafka topic, signaling to other services like manifest or label service that a new order is ready for the next step. This is a classic example of a multi-step distributed transaction coordinated via service calls and events.
You mentioned optimistic locking earlier for consistency. How does the order service manage concurrency when multiple things might be trying to update the same order?
The order's JPA entity in the order service is annotated with @version. This enables optimistic locking managed by Hibernate JPA. This is crucial for maximizing concurrency. When a conflict occurs, for example, if 2 services try to update the same order simultaneously, maybe one cancels it while another tries to ship it, the second transaction attempting to commit will receive an object optimistic locking failure exception. The service logic is designed to catch this specific exception and then typically retry the business operation after reloading the latest version of the ordered data. This ensures that valid updates eventually succeed without needing pessimistic locks that would serialize access and hurt performance.
Okay, that covers orders. Next up is the inventory sync service. This sounds vital for keeping track of stock across potentially many different sales channels integrated via platform sync.
It absolutely is. The bounded context of this service is to maintain a consistent, albeit eventually consistent, view of product stock levels across all sales channels. It uses CRDTs, conflict-free replicated data types, to achieve stronger eventual consistency guarantees, especially important in a distributed multi-channel environment where updates can come from many places.
Tell us more about this CRDT-based inventory model. How does it handle updates and potential conflicts without losing track of stock?
It uses a specific type of CRDT called a PN counter, positive-negative counter, for inventory quantities. A PM counter allows increments and decrements originated from different replicas, or services in this case, to be merged correctly, regardless of the order they arrive in. Crucially, each update, for example, +1 sold, -1 returned, doesn't just send the new quantity, it includes a vector clock. This vector clock contains information about the source of the update and its logical time. For conflict resolution, it relies on this vector clock comparison rather than a simple last right wins, LWW strategy. LWW can lead to lost updates if two updates happen near simultaneously and one overwrites the other due to slightly different system clocks. Clock skew. Vector clocks allow the system to determine the causal history of updates. Did update A happen before update B, or are they concurrent? And merge them correctly based on the PN counter logic, providing stronger eventual consistency guarantees and preventing lost sales or overselling due to data inconsistencies. The service consumes normalized inventory updates from Kafka, sent by Platform Sync Service, applies the CRDT merge logic, and stores the resultant state, probably in DynamoDB for scalability, maybe with the serialized CRDT state and vector clock.
That's a really sophisticated way to handle inventory. Now to the label service, which sounds like the final, crucial transaction step in getting a package out the door. This must be rock solid.
It is, and its bounded context positions it as the transactional endpoint for fulfillment, handling the final carrier booking and shipping label generation. This service is designed with incredibly robust failure handling due to its critical nature. A failure here directly impacts shipping.
What's the core logic for generating a label, and how does it handle potential failures in such a multi-step process involving external carriers?
This is where the label generation saga with complete failure handling comes in. It's implemented as a multi-step distributed transaction, often orchestrated using a saga pattern. 1, it receives a generate label request, often via a gRPC call from the order service or maybe a manual trigger. 2, it might first call the courier service to reserve a tracking number from the chosen carrier's pool. 3, then it calls the carrier-specific API via the appropriate courier adapter service to formally book the shipment with all the details: address, weight, dimensions, service type. This is usually the riskiest step. 4, if booking succeeds, it generates a PDF label in the carrier's required format, often using a third-party library or an internal rendering service. 5, it then uploads this label PDF to Amazon S3 for persistent storage, getting back the label's 3 path. 6, it updates the shipment status in its own PostgreSQL database, sharded by Celeread, to label generated or shipped, storing the tracking number and S3 path. 7, finally, it publishes a shipment created event or label generated event to Kafka, signaling to other services like tracking.
That's a lot of steps, and that call to the carrier API seems like a major point of potential failure. What if multiple requests try to generate a label for the same shipment concurrently?
Good point. It uses distributed locking. Specifically, it employs Redis to acquire a distributed lock using the shipmented or ordered as the key, probably with a short TTL, like 5 minutes. This prevents concurrent label generation attempts for the same shipment, which could lead to duplicate bookings or tracking numbers with the carrier, causing confusion and extra cost.
Okay, locking prevents duplicates. But what if any of those steps in the saga fail? Like booking succeeds, but the PDF generation fails, or S3 upload fails.
This is where compensating transactions are absolutely critical. For each major step in the label generation saga that has external side effects, like booking the shipment, the label service implements a corresponding compensating transaction. So if the carrier booking succeeds, step 3, but then the label PDF generation fails, step 4, the saga orchestrator, or the service logic itself, triggers a compensating action to automatically cancel the shipment booking with the carrier via another API call. This ensures that the system always returns to a consistent state. You don't have a book shipment with no label. It also incorporates idempotency handling, where all label generation requests likely include a unique idempotency key, may be generated by the order service. The label service checks this key, perhaps against Redis or its database, to prevent duplicate processing if the same request is accidentally sent twice due to network retries. This combination of sagas, compensating transactions, and idempotency is a masterclass in handling distributed transaction failures reliably.
That makes sense. It sounds like a lot of thought went into preventing partial failures. What about managing manifests and pickups? Are those separate?
Yes, those are handled by newer dedicated services following the same DDD principles. There's a manifest management service. Its bounded context is generating, managing, and distributing the shipping manifests required by carriers for pickup. It groups shipments by carrier, pickup location, schedule, applies carrier formatting rules, and generates PDF manifests.
And scheduling the actual pickup.
That's the pickup scheduling service. It manages scheduling pickup requests with carriers, handling time slot availability, often pulled from carrier APIs, specific constraints like minimum shipments, and coordinating with the manifest service. Both likely use PostgreSQL, sharded, and communicate via Kafka events.
Let's move to the post-fulfillment and support domain, starting with the tracking service. This must be vital for customer satisfaction. Everyone wants to know where their package is.
It is, and its bounded context is to own the state and history of a shipment after a label has been generated, supported by a robust data pipeline architecture to handle updates from many sources.
How does it ingest tracking data from so many different carriers? This sounds like a complete data pipeline challenge in itself.
It's a comprehensive, multi-source ingestion pipeline designed for reliability. First, there's webhook ingestion, with dedicated POST internal webhooks tracking endpoints, possibly unique per carrier, to receive real-time updates as shipments move through the carrier network. This is the preferred method. Second, for carriers that don't offer reliable webhooks, there are dedicated internal polling services. These periodically call the carrier's tracking API, using the tracking number, to fetch the latest status for shipments that haven't reached a final state. Third, sellers can also initiate seller-initiated updates manually through the UI for certain edge cases or disputes.
Okay, so raw data comes in via webhooks or polling. Once that raw data is ingested, what happens? How does it make sense of it?
The tracking data processing pipeline takes these raw tracking events from various sources, Kafka topics fed by the webhook handlers and pollers, normalizes them into a consistent internal format using Avro schemas again, enriches them, for example, by adding locality information based on the scan location using the address validation service, and then processes them. It implements a formal state machine architecture using something like Spring State Machine. This defines valid state transitions, Picked up can transition to in transit, but not directly to requested. This state machine logic is crucial for understanding the shipment's journey. Based on state transitions and specific event patterns, like delivery attempted recipient unavailable, it performs automatic NDR non-delivery report detection. It also recalculates the EDD, estimated delivery date, dynamically as the shipment progresses or faces delays. Furthermore, it monitors carrier performance against SLAs, service level agreements, based on the timestamps of these tracking events. It also monitors the quality of data received from each carrier.
That leads nicely to the NDR non-delivery report management service. This sounds particularly important for the Indian market, dealing with failed delivery attempts.
It is critical. The bounded context of this service is specifically designed for the complexities of the Indian market, handling the workflow for failed deliveries with advanced automation. This is crucial given the higher rate of non-delivery attempts that can sometimes occur due to addressing issues, customer unavailability, etc.
How does it actually detect an NDR? Does it wait for the tracking service?
For NDR detection, it primarily consumes shipment events from a Kafka topic produced by the tracking service. When the tracking service's state machine detects a pattern indicating a non-delivery, like multiple failed attempts or a specific undelivered scan, it publishes a specific event, maybe shipment.undelivered. The NDR service consumes this event and creates a new NDR record in its database. This creation might be governed by a configurable rules engine, for example, defining that 3 failed delivery attempts within 2 days equals an NDR, or specific carrier codes trigger it.
And once an NDR is detected and a case is created, what automation does it trigger? Does the seller have to manually intervene every time?
Not necessarily. It has a powerful automation engine that uses a rules-based system configured by the seller. Based on these rules and the reason for non-delivery, it can automatically reattempt delivery, instructing the carrier via the courier service, try to redirect shipments to alternate addresses it provided, initiate returns, RTO, after a certain number of failed attempts, and notify sellers through their preferred channels, email, SMS, dashboard, about the NDR and any actions taken. This significantly reduces manual intervention for sellers. It also integrates with the Sense RTO, Return to Origin score, and internal ML service for RTO prevention. It uses the predicted RTO risk score to prioritize high-risk NDR cases, perhaps triggering faster seller notification or different automated actions to try and prevent the shipment from being returned, which is costly. The strategic insight here is that automation isn't just about efficiency, it's about directly impacting the bottom line by preventing costly returns.
That makes a lot of sense. What about managing returns when they do happen?
That's handled by the return management service. Its bounded context is managing the entire reverse logistics process, from a customer initiating a return request to the item being received back and a refund being processed. It has its own state machine, requested, approved, picked up, QC'd on, refunded, integrates with tracking for updates, and crucially, integrates with the account service for processing refunds after quality checks.
And compliance, what about invoices and taxes?
There's an invoices and GST management service. Its bounded context is handling the generation and management of GST-compliant invoices for shipping charges, COD fees, etc. It has a GST calculation engine, generates PDF invoices, ensures proper numbering and compliance rules are followed, storing invoice details in PDFs.
Okay. Finally, let's look at some additional critical services, specifically the Sense ML Intelligence Service. This sounds like the brains behind some of Shiprocket's predictive capabilities we hinted at.
It absolutely is. The bounded context of the Sense service is the machine learning platform that powers predictive analytics used across Shiprocket, primarily for RTO, return to origin scores, and enhancing address validation.
How does it predict RTO? What goes into that model?
The RTO prediction model is quite sophisticated. It features extensive engineering, combining historical data, things like order value, product category, historical success rate for that PIN code, payment method, CIT is often higher risk, address quality score with real-time data like current NDR patterns and seasonal trends. For model serving, it uses TensorFlow serving, which allows for efficient, high-performance deployment of machine learning models via API endpoints. They use Canary deployment for rolling out new model versions safely. It likely incorporates continuous online learning, where model weights are periodically updated based on actual RTO outcomes from recent shipments, allowing the model to adapt to changing trends. Finally, it provides explainability, maybe using techniques like SHAP values, to offer feature importance scores. This helps sellers understand why a particular shipment was flagged as high RTO risk, building trust. This level of practical ML integration is a huge differentiator.
That's a very advanced approach. What about the address quality scoring we mentioned earlier?
For address quality scoring, Sense performs deeper analysis than the basic validation service. It uses geospatial analysis, comparing the address coordinates or PIN code against known delivery boundaries and historical delivery success rates for that specific micro-locality. It also applies NLP, natural language processing techniques, to identify potentially incomplete, ambiguous, or misspelled address components, like street names or landmarks. The service then returns a consolidated confidence score from 0 to 100, indicating the likelihood of successful delivery based on all these factors. This score is used both proactively, warning sellers about potentially bad addresses, and reactively, feeding into the RTO model.
And what's this MCP, or multi-step control process? That sounds intriguing.
The MCP, multi-step control process, is likely a more experimental or advanced feature. It uses natural language processing to understand complex user queries or requests, maybe entered in a chat interface or support tool, and translates them into a sequence of internal API orchestrations. It figures out which backend services need to be called, in what order to fulfill the request, and potentially handles error recovery if one step fails. Imagine asking, what's the status of my TOD reconciliation for last week's delivery shipments? And the MCP figures out it needs to call the report service, filter by carrier and date, check the reconciliation service, and synthesize an answer. It's about automating complex operational queries.
Fascinating. Now, a quick word on other critical services that follow similar architectural patterns but fulfill distinct business functions. We have services like the seller onboarding and KYC service, managing signups and verification, the reports and reconciliation service, aggregating data for analytics and financial checks, and potentially a warehousing and fulfillment service if Shiprocket offers those services directly. While each has unique business logic, they leverage the same core technology stack: Spring Boot, PostgreSQL, sharded where needed, Kafka, Redis, and adhere to the same architectural principles of microservices, DDD, robust failure handling, and operational completeness. This consistent approach across all these services is a key factor in Shiprocket's ability to build, maintain, and scale rapidly.
Absolutely. That standardization is crucial for managing such a complex ecosystem effectively.
Wow, that's an incredible amount of detail on all the microservices, showing how they handle distinct parts of the business. It really highlights the complexity, but also the elegant solutions driven by those core principles. Now let's connect all these pieces together and talk about part 4, the data and eventing backbone of Shiprocket's backend. At the heart of this, as we've heard many times, is the Kafka topic architecture.
That's right. Kafka is truly the central nervous system of Shiprocket's asynchronous architecture. It's used for all asynchronous communication between microservices, for event sourcing patterns in some domains, and as the entry point for data pipeline ingestion. A critical design choice here, as mentioned, is the use of Avro for schema enforcement. Avro schemas, managed via a central schema registry, like Confluent Schema Registry, provide a compact binary format and strict contracts for all event data. The registry performs compatibility checks when schemas evolve, ensuring that producers and consumers remain compatible and preventing runtime errors due to unexpected data formats. This schema enforcement is a huge lesson for any new CS student. Define your data contracts clearly, enforce them, and manage their evolution carefully.
So we've talked about how various services produce and consume messages from Kafka. Can you give us a few more examples of key Kafka topics that drive the system, maybe highlighting the partition keys?
Certainly. Let's revisit a few and add some others. Normalized orders. Produced by platform sync service, consumed by order service. Partition key. Partition key. Cellarid. Ensures orders for one seller are processed sequentially by the order service. Retention. 7 days. Normalized inventory updates. Platform sync inventory sync service. Partition key. Cellarid plus SKU, perhaps, or just SKU. Ensures updates for the same item are processed in order. Retention, 7 days. Wallet recharges. Payment service, a LADR service, return service, notification service, analytics, partition key, shipmented or tracking number, shipmented or tracking number. Retention, 7 days. Platform sync commands, maybe inventory sync service, platform sync service, OEG, push this inventory update to Shopify, partition key, Cellarid plus platform type, retention, 24 hours, commands are transient, financial events, account service, reconciliation service, reports service, analytics service, contains detailed ledger events, partition key, retention, 90 days or more, audit requirements, NDR service, Angent service for model training, analytics, partition key, entered, caseed, or shipmented, retention, 7 days, orders created, order service, manifest service, analytics, partition key, retention, 7 days, compensating transactions, DLQ, various services via Saga coordinators, DLQ, processor financial ops team, partition key, original transaction, retention, 30 days for investigation. This DLQ is crucial for catching failures and failure handling platform events. Raw events from platform, webhooks pulling, platform sync service. Partition key might vary. Retention, 24 hours. Each topic is carefully designed with appropriate partitioning, replication factor, usually 3 for resilience, and retention policies based on its purpose and criticality.
That's a comprehensive list, really demonstrating how Kafka ties everything together. And you mentioned exactly one semantics before, particularly for finance. Can you explain in a bit more depth how this is achieved for critical topics? It sounds complex, but vital for ensuring no message is ever lost or duplicated during processing, even if services restart or fail.
It is sophisticated and a common challenge in distributed systems that requires careful configuration on both the producer and consumer side, along with Kafka broker settings. Exactly once means that despite potential network issues, broker failures, or service restarts, each message is processed once and only once from a business logic perspective. To achieve this for critical topics like wallet recharges or financial events, several Kafka features and configurations are leveraged together. 1. Kafka transactions are enabled for producers writing to these critical topics. This allows a producer, like the payment service, to send a batch of messages, potentially to multiple topics or partitions as a single atomic unit. It wraps the send calls within a transaction. If any part of the send operation fails before commit transaction is called, all messages in that transaction are effectively rolled back and won't be visible to consumers. 2. Consumers are configured with isolation level read committed. This setting ensures that consumers, like the account service, only read messages that are part of a fully committed transaction. Messages that are part of an ongoing or aborted transaction are simply invisible to these consumers, preventing them from processing incomplete or rolled back data. 3. Producers use idempotent producers. Kafka producers can be configured to be idempotent, meaning that if the producer sends the same message multiple times due to retries, for example after a network error, the broker will detect the duplicate using sequence numbers and ensure the message is only written to the log once. This prevents duplication at the broker level. 4. Consumers commit offsets transactionally. When a consumer, like the account service processing a wallet recharge, successfully processes a message or batch of messages and commits the corresponding database update, it commits its Kafka offsets, its current reading position, as part of that same database transaction or within the Kafka transaction context if using Kafka streams exactly once. If the service crashes after processing the message but before committing the offset, upon restarting, it will reread and reprocess the same message. However, if it crashes after committing the offset, it will start from the next message. This transactional offset commit ties the message processing and the offset update together atomically. These 4 elements, producer idempotent site transactions, consumer isolation level, and transactional offset commits, work in concert to provide a strong guarantee of exactly once processing semantics, crucial for financial and critical order-related data where duplication or loss is unacceptable.
That's an incredibly robust Kafka setup, really thinking through the failure modes. Now, let's talk about the analytics data pipeline, specifically how operational data gets into the analytics systems reliably using change data capture, CDC. This needs to happen without impacting the performance of the production databases that the backend services rely on.
Exactly. This pipeline is vital for business intelligence, reporting, and machine learning model training, and it's designed for comprehensive failure handling and minimal production impact. The first step involves Debezium with reliability enhancements. Debezium connectors are deployed in a dedicated Kafka Connect cluster, separate from the main application infrastructure. These connectors capture change data capture CDC events directly from the transaction logs, like write-ahead logs or WALs of Shiprocket's production PostgreSQL databases and potentially from DynamoDB streams. These Debezium connectors are configured with dead letter queues, DLQs, for any events that fail during processing or serialization, ensuring no data change is silently lost. They also have robust offset management, storing their position in the transaction log persistently, often in Kafka itself, to automatically recover from failures and resume from where they left off. They also handle database schema evolution gracefully, often integrating with the schema registry.
So Debezium essentially listens to the database changes without querying the tables directly. How does that work exactly?
The change data capture process involves Debezium reading the database's native transaction log. This log records every single change made to the database, inserts, updates, deletes, before it's even written to the tables, ensuring durability. Debezium interprets these low-level log entries, converts them into structured event messages, typically in Avro or JSON format, including before and after images of the data, and publishes them to dedicated Kafka topics, one topic per database table usually, e.g. dbz.public.orders, dbz.public.shipments. This process is non-intrusive to the operational databases because it reads the logs, which the database produces anyway for replication and recovery. It doesn't add significant load to your primary application databases compared to, say, query-based CDC.
Okay, so those raw CDC events representing every database change are now in Kafka. They probably need to be cleaned up or transformed for analytics, right?
No, exactly. That's the data transformation layer, often implemented using Kafka Streams applications or sometimes Spark streaming or Flink jobs. These stream processing applications consume the raw CDC events from the Debezium topics. They perform transformations like filtering out intermediate technical updates, joining streams from different tables, EPC joining order events with shipment events, enriching data with information from other services, maybe via API lookups or cache data, and aggregating data into more business-friendly formats or metrics. They often handle event time processing, meaning they consider the timestamp when the change actually occurred in the source database, not just when it was processed downstream. They use techniques like watermarks to manage late-arriving data and might perform deduplication using event timestamps and unique IDs from the source change records to ensure data quality.
And from there, the transformed data goes to the data lake and eventually into formats suitable for reporting and dashboards.
Yes. The next step is often data lake ingestion. A Kafka Connect S3 sync connector consumes the transformed data streams from Kafka and writes them efficiently as partition files, for example, partition by date, in an optimized format like Parquet into Amazon S3, which serves as the data lake. Finally, data warehouse loading might involve tools like AWS Glue ETL jobs or dbt data build tool models. These read the data from the S3 data lake, apply further transformations to create dimensional models, fact and dimension tables, suitable for analytical querying, perform data quality checks, and load the results into a data warehouse like Amazon Redshift or Snowflake. The analytics service, which might be part of the report service, then provides a REST API for internal dashboards or reporting tools, querying the data warehouse, often with query caching and rate limiting built in. This entire pipeline from database transaction log to dashboard is designed for reliability and scalability, decoupled from the production services.
That's a very robust and modern data pipeline for analytics. Finally, let's revisit shard management and rebalancing, especially given how critical database sharding by Celerid is to Shiprocket's ability to scale its core PostgreSQL databases.
Indeed. The sharding strategy overview, just to reiterate, it's primarily logical sharding by Celerid applied across most tenant-specific data: orders, shipments, returns, account balances, etc. This means the application code, using a routing layer, maybe a custom Spring data source router, determines which physical database shard holds the data for a given Celerid. For very high-volume sellers, this might translate to them having their data reside on dedicated physical database instances for better isolation, but the principle is distributing sellers across multiple independent databases. A consistent hashing algorithm is typically used for assigning seller IDs to shards. This ensures a relatively even distribution and, importantly, minimizes data movement when shards are added or removed. Only a fraction of sellers need to be potentially relocated.
Why is shard rebalancing actually needed? And how is it done without causing major disruption? Sounds risky.
Shard rebalancing becomes necessary over time to address hotspots, some shards becoming much busier than others due to uneven seller growth, or when new physical shards are added to increase overall capacity, or perhaps when old ones are decommissioned. It's a critical, detailed implementation that needs to be done carefully. It usually involves a controlled background process that migrates sellers, or rather their data, in small batches, typically during off-peak hours to minimize impact. The process generally involves several steps. 1. Identifying sellers to move. Based on load metrics or capacity planning, identify a batch of seller IDs to migrate from a source shard to a target shard. 2. Block writes briefly or use dual writes. Either briefly make the seller's data read only on the source shard or implement a dual write mechanism where updates go to both old and new shards during the copy phase. 3. Copy data. Copy all data associated with the selected seller IDs from the source shard to the target shard. This needs to be done consistently. 4. Update routing. Once the copy is complete and verified, update the application's routing layer, the mapping of seller read to shard, to point to the new target shard for these sellers. 5. Switch reads writes. Direct all new traffic for these sellers to the target shard. 6. Cleanup. After a verification period, delete the old data from the original source shard. This multi-step process, often automated with careful monitoring and rollback capabilities, ensures a relatively smooth migration with minimal downtime for the affected sellers.
And what about maintaining consistency when an operation might need data that's spread across multiple database shards? For example, maybe an analytics query needs data from sellers on different shards. That sounds like a huge challenge.
Cross-shard data consistency handling is indeed complex, and generally, systems try to design bounded contexts and sharding keys to minimize the need for real-time cross-shard transactions. For transactional integrity within a single operation that inherently spans shards, which should be rare in a well-designed system, you typically avoid distributed database transactions like two-phase commit due to their complexity, performance overhead, and potential for blocking. Instead, you rely on patterns we've discussed. 1. Eventual consistency via Kafka, the primary mechanism. Service A on shard 1 performs its action and publishes an event. Service B on shard 2 consumes that event and performs its corresponding action. Consistency is achieved eventually. 2. Sagas with compensating transactions. If an operation logically spans shards and requires atomicity, a saga pattern coordinated via Kafka or an orchestrator ensures that if one part fails, compensating actions are triggered on other shards to maintain overall consistency. 3. Materialized views or data replication. For read operations or analytics that need a unified view across shards, data might be asynchronously replicated or aggregated into a separate reporting database or data warehouse, as per the CDC pipeline, where cross-shard queries can be performed without impacting the live transactional shards. The key is usually to accept eventual consistency for cross-shard operations where possible, and use sagas or asynchronous processing for workflows that require coordination, rather than trying to enforce strict, real-time distributed transactions across independent databases.
All right, that makes sense. Focus on keeping transactions within a shard where possible, and use events and sagas otherwise. This brings us to part 5, ensuring backend reliability and operational excellence. This isn't just about building features, but building them to last and perform reliably under pressure. Let's start with the CI/CD pipeline, described as using GitOps with reliability testing. How does this ensure a backend developer's code is deployed safely and reliably?
It is absolutely fundamental. Our CI/CD pipeline is fully automated using tools like GitLab CI and FluxCD for GitOps deployment to Kubernetes to ensure safety, speed, and consistency for every backend code deployment. Crucially, comprehensive reliability testing is integrated at every single stage. The key takeaway here is that reliability isn't an afterthought checked manually before release. It's a measurable output of a well-designed, automated development and deployment process.
Okay, walk us through the typical steps that a backend developer's code goes through from commit to production.
It starts with 1. Code commit. A developer pushes their feature branch containing their Spring Boot service changes to GitLab. This automatically triggers 2. Merge request and CI. When a merge request is created, a GitLab CI pipeline runs. This pipeline is extensive and acts as a quality gate. It runs unit tests, standard JUnit and Mockito tests specific to the developer's code changes, integration tests, tests that interact with real but test-scoped database instances, Kafka, or mocked external services using tools like test containers, static analysis, using SonarQuery, checking for code smells, bugs, vulnerabilities, and adherence to coding standards with a strict quality gate that must pass. Security scan, using tools like OWASP dependency check for vulnerable libraries and potentially DAST dynamic application security testing like OWASP ZAPI against the running service in the CI environment. Load testing. A subset of load tests using Locust might run against the service within the CI environment to catch performance regressions early, maybe simulating 10,000 requests per second for critical endpoints. Chaos testing. Basic chaos mesh experiments might be triggered even here, simulating simple failures like pod deletion or network latency to the database, ensuring basic resilience is built in. Only if all these checks pass can the merge request be approved.
Wow, so a lot of automated testing happens even before the code is merged. What happens after the merge?
Upon a successful merge to the main branch, another pipeline runs for 3. Build and push. It uses Spring Boot's native build image goal, leveraging cloud-native build packs, to create a lean, optimized, OCI-compliant container image for your service without needing a complex Docker file. This image is then tagged with the commit hash or version number and pushed to our private Amazon ECR, Elastic Container Registry. The next step is 4, update manifest. The CI pipeline automatically updates a Kubernetes deployment.yaml file, or Helm chart values file, stored in a separate Git repository dedicated to infrastructure configuration. It changes the image.tag for your specific service to the newly built version. This commit to the config repo is the trigger for deployment. This is the core of GitOps. Git becomes the single source of truth for the desired state of the cluster.
Okay, so the config is updated in Git. How does it actually get deployed to staging and then production?
That's handled by FlexCD, a GitOps controller running in the Kubernetes cluster. 5. Staging deployment. FluxCD continuously monitors the configuration Git repository. When it detects the change to the deployment manifest for your service, it automatically pulls the change and applies it to the staging Kubernetes cluster, rolling out the new version of your service there. In staging, a whole new, more comprehensive suite of tests runs. Automated end-to-end tests involving multiple services, more rigorous performance benchmarks, and more complex chaos experiments targeting interactions between services. 6. Production deployment. Only after passing all staging tests and potentially requiring manual approval is the deployment promoted to production. This promotion might involve updating the config in a production branch of the Git repo. FluxCD then applies the change to the production cluster. Crucially, production deployments follow a canary strategy. The Kubernetes deployment is configured, perhaps using native features or Istio, to initially route only a small percentage of live traffic, c.g. 5%, to the new version pods. Monitoring systems, Prometheus, Grafana, continuously compare key metrics, latency, error rates, resource usage between the old, stable, and new Canary versions of your service. If the Canary metrics remain healthy for a defined period, the rollout gradually proceeds, increasing traffic to the new version until it reaches 100%. If at any point the Canary metrics degrade significantly, an automatic rollback is triggered, shifting traffic back to the stable version and alerting the team. This ensures that problematic deployments have minimal impact on users.
That level of automation and safety netting in the CI/CD pipeline is really impressive. Now, even with all that testing, things can still go wrong in production. Let's talk about comprehensive operational runbooks. How does a backend developer respond when, say, Prometheus fires an alert about latency spikes when their service calls a carrier API?
Good question. Runbooks are essential. They are detailed, step-by-step guides for handling specific operational incidents impacting backend services. They aren't just for the ops team. Backend developers are often involved in diagnosing issues with their services. Let's take your scenario. Carrier API latency spike, for example, FedEx API. Detection, automated. An alert fires in Prometheus Alert Manager. For example, P99 latency of Istio request duration milliseconds bucket destination service fedex-adapter-service.prod.svc.cluster.local, 5,000 mirrors for 5 meter. This alert might be automatically routed to the relevant team's PagerDuty or Slack, possibly enriched with links to relevant Grafana dashboards and Jaeger trace data. Diagnosis, using the runbook. The on-call developer follows the runbook. 1. Check the Grafana dashboard specifically for the FedEx integration, part of the courier service domain. Are we seeing a high error rate as well? Is Istio actively ejecting the FedEx endpoint due to failures? Check Istio upstream active or circuit breaker metrics. If Istio is ejecting it, it means your service isn't even trying to call the failing endpoint anymore, which is good self-preservation. 2. Check the Jaeger UI for distributed traces originating from your courier service or the specific FedEx adapter service, making calls to the external FedEx API. Look for traces with high latency. Is the time being spent on the wire network latency, or is it time spent within the FedEx API server itself, server processing time? This helps pinpoint the source. 3. Check Splunk or Loki logs for your courier service or adapter service. Are there specific error messages, client-side timeouts, connection refused errors? Correlate logs with the slow traces found in Jaeger using the trace ID.
Okay, so using Grafana, Jaeger, and logs helps pinpoint the issue. What immediate actions can the developer take based on the runbook?
The runbook would list potential immediate mitigation steps. 1. Adjust circuit breaker, Istio. If the FedEx API is slow but not entirely down, maybe temporarily increase the Istio circuit breaker thresholds, e.g. allow slightly longer timeouts or more consecutive errors before tripping. If business context allows, to prevent legitimate traffic from being blocked too aggressively by your service. Or, conversely, make it more aggressive if cascading failures are a risk. 2. Feature toggle. If the latency is impacting a non-essential feature that relies on FedEx, for example, fetching detailed tracking substatus, use a pre-built feature flag to temporarily disable that specific functionality within your courier service, degrading gracefully instead of failing completely. 3. Traffic routing, Istio application logic. If possible and configured, use Istio traffic routing rules or application-level logic within your courier service to temporarily shift a higher percentage of shipping volume away from FedEx towards alternative carriers that are performing normally. These actions aim to stabilize the system and minimize user impact immediately while the root cause is further investigated.
And after the immediate fire is out.
The runbook also mandates root cause analysis, RCA, potentially involving communication with the carrier, identifying long-term prevention measures, for example, improving monitoring, adding more resilient timeouts in the adapter service code, requesting API improvements from the carrier, and documenting the incident in a post-mortem. The goal is always to learn from incidents and continuously improve the resilience of your back-end service and its integrations.
This level of detail in operational runbooks is truly impressive. It makes me wonder, how do they ensure this level of reliability is actually designed in and validated proactively? That brings us to the comprehensive reliability testing framework. It's not just testing functionality, but testing resilience.
Exactly. Reliability is not just a goal. It's a quantifiable outcome of a rigorous testing framework that operates at multiple levels, deeply integrated into the development lifecycle.
Let's break down that strategy. How do you test reliability at different levels for back-end services?
The reliability testing strategy covers 4 main levels. 1. Unit level. Within your Spring Boot service code using JUnit Mockito, you write tests specifically for failure scenarios. For example, test how your code behaves when a gRPC call to another service throws an exception, or when a database query times out. You mock these failures and assert that your code handles them gracefully, e.g. returns a default value, retries correctly, throws an appropriate business exception. 2. Service level. This involves testing your individual microservice in isolation or with mock dependencies, but under realistic failure conditions. This is where chaos experiments targeting your specific service, like killing pods, injecting latency to its database, are combined with load testing to identify performance bottlenecks and resilience weaknesses within that service boundary. 3. System level. This expands the scope to test interactions between multiple backend services. End-to-end chaos experiments simulate complex failure scenarios, like a network partition between the order service and the account service during order processing, or a cascading failure originating from a slow carrier API. This validates cross-service resilience. 4. Production level. As discussed in CI/CD, this involves controlled chaos experiments run directly against your deployed services in production during off-peak hours with limited blast radius, and leveraging canary deployments with automated analysis of reliability metrics, error rates, latency for automatic rollback.
That's a very layered approach. Can you go into more detail about how they implement load and stress testing, specifically for the back-end services? What tools and metrics are key?
For load and stress testing targeting back-end services. Tools. They use Locus primarily for simulating HTTP traffic against REST APIs. For testing internal gRPC services, they likely use custom Java clients built with the gRPC libraries or tools like gr-test scenarios. These are designed to push the system to its limits, focusing specifically on back-end heavy workflows, simulating peak holiday traffic volumes for order creation and label generation, simulating large seller onboarding spikes hitting the auth and KYC services, stressing bulk order imports via CSV uploads hitting the order service in Kafka, and simulating payment processing peaks impacting the payment and account services, metrics tracked. During these tests, they meticulously track key performance indicators for your specific backend services. Error rate, AG, HTTP5X errors, gRPC internal errors, latency percentiles, P50, P90, P99, P99.9, CPU and memory utilization of your service pods, database connection pool usage or pools getting exhausted, and critically, Kafka consumer lag for topics consumed by your services. Is your service keeping up with the message rate? Pass-fail criteria. There are strict thresholds defined. For example, the error rate must remain below beta 0.1% at the target sustained load. P99 latency must not exceed a specific budget, ISM 500 meters for critical APIs. Resources, CPU memory connections, must not show signs of exhaustion, and Kafka consumer lag must remain under a certain threshold, VRG 1 minute. Failing these criteria blocks a release or triggers performance tuning.
That's very clear and metric-driven. What about the chaos engineering implementation? What are some critical scenarios they specifically simulate to test the resilience of back-end services, like the financial ones?
For chaos engineering, they use Chaos Mesh integrated into their Kubernetes platform. The critical chaos scenarios are directly aimed at validating the robustness of back-end systems under realistic failure modes. Database failover. Simulate a PostgreSQL master node failure for the account service database during a simulated high volume of financial operations. Does the service handle the failover gracefully? Are the compensating transactions triggered correctly if operations were in flight? Is data integrity maintained? Carrier API failure. Simulate a complete outage or extreme latency of a major carrier's API, e.g. FedEx, during a peak label generation load for the label service and courier service. Do the circuit breakers trip correctly in Istio? Does the label services saga pattern correctly trigger compensating transactions, like canceling bookings? Does traffic shift to alternative carriers if configured, network partition? Inject network packet loss or latency between critical services, like the order service and the inventory sync service? How does the system behave? Does Spring Retry handle transient issues? Are user-facing operations significantly degraded? Clock skew. Intentionally introduce clock skew between nodes running instances of the inventory sync service. Does the CRDT logic still correctly merge concurrent inventory updates using vector clocks, or does it lead to inconsistencies? Redis failover. Simulate a Redis master shard failure in the Elasticache cluster during high-volume payment processing that relies on Redis for idempotency checks or distributed locks. Does the application handle the failover transparently? Are any payments processed twice or locks mishandled? After injecting chaos, automated validation scripts run to query application metrics and potentially specific data states to confirm that the system remains stable, recovered correctly, and maintained data integrity, identifying weaknesses in your services before they manifest as production incidents.
It's incredible how they proactively test for these specific failure modes. So how is all this reliability testing unit service system chaos woven into the continuous integration and deployment pipeline we discussed earlier?
The reliability testing integration into CI/CD ensures resilience is built and verified at every single stage. Pre-commit. Developers are expected to run unit tests, including those covering failure scenarios, in their local environment before committing code. Static analysis tools might also run locally. CI pipeline on merge request. As mentioned, this includes automated unit tests, integration tests, including some failure injection via mocks or test containers, basic load testing for critical paths, and potentially lightweight chaos experiments on non-critical failure scenarios, like pod restarts. Reliability metrics are collected during these tests. Staging environment, post-merge, pre-production. This is where the most intensive reliability testing happens before production exposure. Full-scale load testing against realistic traffic patterns, critical end-to-end chaos experiments simulating database failures, network partitions, dependency outages are executed. Automated reliability validation checks metrics against predefined SLOs, service level objectives. Passing these gates is mandatory for production deployment. Controlled chaos experiments might run periodically during off-peak hours against a subset of production traffic. More importantly, the Canary deployment strategy itself is a form of production reliability testing, constantly comparing the metrics of the new version against the stable version, allowing for automatic rollback if the new code introduces reliability regressions, increased errors, latency for your deployed backend code.
That's an extraordinary commitment to reliability baked into the entire process. Now, let's specifically talk about Part 6. Financial integrity and compliance, especially from a back-end developer's perspective. This is where accuracy and trust are absolutely non-negotiable.
Absolutely. The financial domain is where Shiprocket applies its most stringent controls, building on the consistency models and reliability practices we've discussed.
How do they ensure financial controls and maintain an immutable audit trail for every single transaction handled by the back-end services?
For the transaction audit trail, every single financial event or transaction, a wallet recharge, a fund reservation for an order, a fee deduction, a refund, a Sahadi settlement adjustment handled by your payment and account services is meticulously recorded. This isn't just a simple log line, it's a structured, immutable audit log, likely stored in a dedicated table within PostgreSQL, perhaps using append-only permissions or blockchain-like hashing for tamper evidence. The audit trail content is incredibly detailed. It includes a nanosecond precision timestamp, the user ID or service account principal that initiated the transaction, the full request and response payloads, or key parts thereof, the source IP address, if applicable, a unique transaction ID for correlation across systems, linking payment service records to account service records, and potentially the state before and after the transaction. This comprehensive logging ensures complete accountability, traceability, and non-repudiation for every financial action taken by your back-end systems.
Okay, so if there's ever a question about any financial transaction, the full history is there and can be trusted. What about reconciling all these transactions across different systems or with external partners like payment gateways?
Reconciliation is critical. The platform implements an automated reconciliation process that your back-end systems facilitate by providing clean, reliable data streams, often via those financial events Kafka topics or database CDC. The process, likely handled by the dedicated reports and reconciliation service, involves 1. Data collection, automatically gathering transaction data feeds from all relevant internal systems, for example, payment service DB, account service ledger, order service, and external sources. For example, payment gateway settlement reports, carrier COD, remittance files. 2. Matching. Using sophisticated rules and identifiers, transaction IDs, order IDs, amounts, timestamps, to automatically match corresponding transactions across these different systems. 3. Discrepancy identification, flagging any transactions that don't match or are missing from one system compared to another. 4. Root cause analysis, providing tools or data to help the finance team investigate why discrepancies occurred, usually timing issues, processing errors, fee variations. 5. Resolution workflow, facilitating the process of applying corrective adjustments, for example, manual ledger entries, initiating refunds, through approved channels with audit trails. 6. Reporting, generating daily or periodic reconciliation summary reports showing matched transactions, outstanding discrepancies, and aging. This rigorous automated process ensures that the financial data processed by your services is accurate and consistent across the platform and with external partners.
That makes sense. And what happens when a discrepancy is traced back to a technical issue? Or specifically, what about those failed compensating transactions that end up in the dead letter queue we discussed for the account service? What's the process for the financial operations team handling that compensating transactions DLQ?
The DLQ management process for the compensating transactions DLQ, which is populated by failures within your account services Saga logic, is a critical manual safety net. There's a clear documented procedure for the financial operations team. 1. Monitor and review. The team monitors the DLQ daily, or more frequently, via dashboards or alerts. 2. Triage. They assess each message in the DLQ based on its potential financial impact and urgency. 3. Investigate. They use the information in the DLQ message, original transaction details, error messages, and correlate it with logs and audit trails to understand the root cause of why the compensating transaction failed. This might require collaboration with the engineering team responsible for the account service. 4. Resolve. Based on the investigation, they take the appropriate corrective action manually. This might involve manually adjusting a seller's balance, retrying the operation, or escalating a bug fix. All manual actions must follow strict approval processes and have their own audit trails. 5. Verify. They confirm that the manual resolution has successfully corrected the financial inconsistency. 6. Document. All actions taken, findings, and resolutions are documented for audit purposes and to identify recurring issues. This meticulous process ensures that even failures in your automated financial back-end logic are caught, thoroughly investigated, and definitively resolved by humans, maintaining absolute financial integrity.
That's an extremely thorough overview of financial integrity, combining automated controls with essential human oversight. Now, for our final part, let's bring it back to the real world. Part 7. Shiprocket's backend in the real world. India specifics. How is this entire backend architecture specifically tailored for the unique challenges and opportunities of the Indian market?
This is where the architecture demonstrates its deep understanding of its operating environment. It's not just generic logistics software, it's built for India. First, regarding Indian market specifics, the address validation and locality service is heavily optimized specifically for India's unique 6-digit PIN code system. It incorporates detailed regional knowledge about localities within PIN codes, delivery office jurisdictions, and serviceability nuances that are specific to the Indian logistics landscape. This is crucial given the diverse and sometimes less structured addressing patterns found across the country, especially outside major metros. It understands near landmark X might be vital information.
Right, address validation is key. What about compliance?
The Invoices and GST Management Service is built from the ground up to ensure full compliance with India's Goods and Services Tax (GST) regulations, which are notoriously complex and subject to frequent updates. It correctly calculates GST based on HSN codes for different goods, applicable rates, which vary, place of supply rules, and handles special categories. It generates compliant tax invoices with all required fields. This is non-negotiable for operating legally in India.
And the NDR service you mentioned.
Exactly. The NDR Non-Delivery Report Management Service is a critical component uniquely addressing the statistically higher rate of non-delivery scenarios that can occur in the Indian e-commerce market due to various factors: address quality, customer availability, COD issues. It provides specialized automated workflows for reattempts, communication with customers for address correction, handling redirects, and managing returns, RTOs, aiming to maximize successful deliveries and minimize costly returns. This is a perfect example of a back-end system directly solving a significant market-specific business problem.
Beyond compliance and local specifics like PIN codes and NDRs, how is the back-end architected for the sheer scale of Indian e-commerce, especially during peak times like Diwali or the big billion days?
That's where scalability for Indian e-commerce comes in, and it's baked into the design choices we've discussed. The entire back-end architecture leveraging horizontal autoscaling in Kubernetes, EKS, the buffering and decoupling capabilities of Kafka, database sharding for PostgreSQL, the use of scalable databases like DynamoDB where appropriate, and aggressive caching with Redis is designed fundamentally to handle massive, spiky loads, aiming for 10x normal traffic during major Indian festivals like Diwali and Eid or major online sales events. Load testing specifically simulates these peak scenarios. The platform sync service also needs to handle variations like regional language addresses, which might be used by sellers or buyers on various platforms, ensuring pan-India coverage where address data isn't always in English-Latin script. Furthermore, the address validation service, including the ML models and sense, is specifically optimized for Tier 2 and Tier 3 cities and towns, which often have less structured addressing patterns compared to metropolitan areas. The system needs to be intelligent enough to parse and validate addresses that might look quite different from standard formats.
Makes sense. Finally, let's explicitly tie this all back to the business benefits realization. How does this incredibly robust and tailored back-end architecture directly drive the benefits that Shiprocket offers to its business customers?
The back-end is the direct enabler of these value propositions. For reduced shipping costs, it's the courier service back-end logic comparing rates across 15-plus carriers in real time, applying negotiated volume discounts based on aggregated seller volume, and recommending the cheapest option for a given service level. For increased delivery speed, it's the courier service continuously monitoring carrier API performance and potentially deprioritizing slow carriers, the address validation service ensuring accurate routing information to minimize delays, and the pickup scheduling service optimizing pickup times with carriers. For improved customer experience, it's primarily the tracking service providing timely, accurate, real-time updates ingested from multiple sources, and the return management service offering a smooth, automated process for reverse logistics. The reliability of the whole platform contributes here, too.
And for the internal efficiency of the businesses using Shiprocket.
Operational efficiency for sellers is significantly boosted by the platform sync service automating order fetching and status updates, eliminating manual data entry. The centralized dashboard pulling data from various backend services, order, shipment, payment, provides a single view. The address validation service reduces errors and failed deliveries caused by bad addresses upfront. Lastly, data-driven decision-making is empowered by the reports and reconciliation service and the underlying analytics pipeline. These provide sellers with comprehensive, actionable insights into their shipping costs, deliver performance by carrier, RTO rates, geographical trends, etc., allowing them to optimize their logistics strategy based on hard data generated and processed by the back-end systems.
Fantastic. That really connects the deep technical details to the tangible business outcomes. And with that, we conclude our deep dives into the back-end architecture of Shiprocket. We've taken an incredible journey today, really, from the high-level vision and foundational principles through the intricacies of individual microservices like the account service, the label service, the databases they use like PostgreSQL and DynamoDB, the Kafka event streams that connect them all, and the rigorous operational practices like chaos engineering and GitOps that keep it all running reliably at massive scale. You've seen how every decision, from choosing gRPC over REST for internal calls, to implementing CRDTs for inventory consistency, to designing complex financial sagas, is a deliberate choice made to build a highly scalable, reliable, and financially robust logistics platform tailored for a market like India. The back end, as you've now discovered in detail, is truly the invisible engine driving all visible operations, and the depth and quality of its design directly translates to the business's success and the end customer's experience.
Indeed. It's a really impressive testament to meticulous engineering, thoughtful architecture, and a relentless focus on reliability. A fantastic case study in applied computer science, really.
So as you, our listener, embark on your own journey in computer science, maybe building your own projects or joining a team, consider this provocative thought. Building a system like Shiprocket isn't just about writing code in Java or configuring Kafka. It's about making deliberate architectural trade-offs, deeply understanding complex business domains, like logistics and finance, and relentlessly prioritizing reliability and data integrity in every single component. Was one area of this architecture maybe the hybrid consistency model, the CRDT approach, the gateway per carrier pattern, or the chaos testing framework that surprised you the most? And how would you, putting on your architect hat, approach designing that specific component for even greater resilience or perhaps simplicity in the face of the unexpected failures that inevitably happen in the real world? Something to think about. Thank you for joining us on The Deep Dive.